Guys, today we're going to see lessons about work done by variable forces. Okay, so today we are going to study about week 10 for HET pre-physics 1. So it's about work done, so we'll start with work done by variable forces. Okay, to approximate the work done by a variable force Fx, we divide the overall displacement into a series of small displacement, which is delta x. During each small displacement, the work done is, which means change of W is equal to Fx times change of distance, which is we have graphs, that is we have a force here and delta x here. Okay, so the graph can be this like this shape. So if we want to find the work done or total work done, we have to divide this graph into small rectangular shapes. Okay, like this rectangular shapes. I will see, let me show you like a perfect picture like this graphs. Okay, so if you multiply every rectangle that its width and its length and find its area of each rectangle, and if you add all rectangles, then you will find total work done. So on the graph of Fx, which means this graph on the right, each work done or W is the area of a rectangle of height Fx we have, which is the force, and the width we have delta x, which is the displacement. The total work done is the sum of the areas of this rectangle. So if the areas, you will find the area by the area law, which is length times width. So if you add all of this, then you will find the total work done. The total work done is the sum of the areas of this rectangles. Okay, so this approximation gets better as we make the rectangles thinner and thinner. So if we make every rectangle very thin and thinner and thinner and thinner, then the approximation or the value you get is going to get closer to the truth value. Okay, so the total work done is the area under the graph of Fx from xi to xf. Okay, starting from xi up to xf. Okay, to draw back a simple bow, the force the arc exerts on the string. So we have a simple bow. Okay, we have a simple bow, this shape. Sorry, I'm not that good in drawing. So we have a small bow. Okay, so we want to send an arrow. Okay, so we will pull this string to this direction. Okay, when we pulling this string this direction, and it will increase as the displacement of the string increases, the bow bends slightly. So this bow will bend slightly. Okay, the force versus position graph describes such a bow. So this graph here represents the motion of this bow. Calculate the work done by the arc on the string as he draws the string back 40 centimeters. So he is pulling this string 40 centimeter back. So in meter, always we have to change from centimeter to meter because we don't work with centimeter, we have to work with meter. Okay, so this means 0.4 meter. Okay, so this is the graph we have. Now you want to find the work done. So work done is what? Work done. So if you want to find the work done from a graph, you have to find the area under the graph of Fx and x. So when you want to find the area of this graph, it is what type of shape is this? It is triangle. So area of triangle is what? It is half times base times height. So instead of base, you have what here? X, which is a displacement. In displacement, you have 0.4 times the height. You have height how much? Which is the force instead of the height. You have how much? You have 160, I guess. Yeah, 116 Newton. 116 Newton. So if you divide this one, this is 0.2. So the answer will going to be how much? 32 joules, which is positive because if you see the slope of the angle of the graph is positive. Now we'll go to Hooke's law and ideal springs. Okay, so Hooke's law and ideal springs. Robert Hooke, which he was a president or alive from 1635 to 1703, observed that for many objects the deformations, change in size or shape, that means, of the object is proportional to the magnitude of the force that causes the deformation. Now deformation means the change in shape or size of an object, okay, and it's mainly depend on the force that is acting on that object. So if the force is very high compared to the hardness of the object, it will change easily or have a new shape. Okay, so we'll talk about springs or spring now. So in spring we have two types of things there. We have when we stretch a spring or we compress a spring. Okay, so we're gonna see what their difference and how we find the unknown materials on them. Okay, now the first one is Hooke's law for ideal springs. So we have a formula and it is F is equal to K times change of L. Change of L is the change of size or length you are making, which is in here it is represented as X. Okay, if you see this one, it's represented as X. Okay, so when we refer to ideal springs, we mean a spring that is described by Hooke's law. Okay, and we don't mention any spring here. Okay, it has to be ideal spring. Okay, and we take this as massless. Okay, F is the magnitude of the force exerted on each end of the spring, and delta L is the distance that the spring is stretched or compressed from its relaxed length. So relaxed length, if we take this one at the first, like this is a relaxed length. Now if it's stretched, it will take a lot of space. So this is the X, or here we are taking as delta L. Okay, or it may compress it. Okay, so this will be the X, but we will take in negative. Okay, we will show you how we will this one. The constant K is called spring constant for a particular spring. Okay, K is called spring constant. For every spring, K has its own value. Okay, for exerted by ideal spring, Hooke's law. So we have F X is equal to minus K X. Okay, this is one formula. We're gonna use this formula for a lot. We'll talk about it later. Fx is the force exerted by movable end when its position is x and the spring is relaxed at x is equal to 0. This is known fact. Okay, let's start now. Work done by ideal spring. So in here, how can we find the work done by ideal spring? So we will talk about work now. Work done. Okay, work done by ideal spring. So if you want to talk about work by ideal spring, we have to look at the graph of the spring. Okay, so the graph of ideal looks like this. Okay, so we have the distance or the final x starting from the initial, we put it here. So the graph is going into negative. Okay, minus kxf. So fx. So why is going to negative? Because when you apply a force